everyone. We're going to continue what we started just a little bit in class today, starting to talk about acids and bases. So we're going to end up doing page 7 and 8 in our notes. You also want to have your reference table near you, so you can look at tables K and L. And let me pause. Okay, so in class, we had talked about that. Okay, so when you look, I've shown you this in class. Some of you got further than others. I kind of want to think that when I'm looking at these table Ks and table Ls, that, and I don't know if we wrote this down in your class personally, but strong acids are going to be at the top, and weak acids are going to be at the bottom. We have some things that are going to be weird. We talked about how we can tell, we see H's, so acids are going to have H, and bases, you can see I underlined OH, so bases have OH minus. That's important to note. We have a few exceptions. We have a star by aqueous ammonia. I'll put another star there. That doesn't look like the others, but it is a base. Again, with the bases, I go from strong to weak, so if they're ever asking you about that. And then with my acids, I have this, they rewrote this bottom one with this COOH. That actually is an organic acid. It'll be weird. I can see that they also wrote it for me with the H in front to make it look more like an acid. So in general, you want to think acids have H, bases have OH. And I think it's time for us to move on. All right, next page. Okay, so we are on our packet, page 7. This is in the new acid-base section of your packet, so you can flip to the tab. And at first, we want to start out with our acid-base definitions. So our acid-base definitions, we had already seen a couple things on table K and table L. So we're going to note that table K has your common acids. Table L has your common bases. So table K and table L will be very important to us. We looked at table K first and talked about our acids. And technically what I was referring to was the Arrhenius definition of acids. The Arrhenius definition is the most common and means an Arrhenius acid has an H, which we saw on table K, and it releases H plus ions into aqueous solutions. H plus, remember, it lost an electron, so it really forms protons that are in there. They will refer to H plus as a proton much more often in this unit. These attach to H2O to form H3O plus, which is hydronium. I want to remember that hydronium is on table E. It's a polyatomic. And what happens is I would have H2O, and I have a little H plus floating around. What happens is H plus sees these electrons and says, hey, can I jump on there? And then it says, yeah, sure. And so what I really have now, if I go over this diagram of H3O plus, I'll now have an O that has 3 H's attached to it with 2 electrons, and technically it will have a positive charge. So you want to know that H3O plus would also be something to look for because that's how it attaches to your water. That's called a coordinate covalent bond, where it says diagram another. We don't have to do that, but it is coordinate covalent because basically it's giving electrons to that proton. The example reaction for that was I had H plus going to H2O, which forms me H3O plus. This section, I'm going to actually leave blank right now. Don't do that right now. We're going to talk about our bases. Oh, wait, go back to your acids. I want to put on the side. Acids, big takeaway. Acids, you're going to look for H plus or H3O plus. You're looking for those ions to be in there. And you want to remember that this is called hydronium. This often is called a proton or your hydrogen ion. So that will be important. Okay, so now to our bases. For our bases, an Arrhenius base is defined as having an OH and releases OH minus ions in aqueous solutions, which form OH minus is called hydroxide. I can get that right from table E. So it forms a hydroxide ion. So fill that in, ion. And these hydroxide ions are the only negative ions that I will see in solution if I have a base. So what happens is acids and bases are going to break up when you put them into water. You're going to find that OH minus ion. You won't have any other that are negative. So examples, it says, let's look at table L, which we already did. And from table L, we know, we'll write on the side, bases, big takeaway, have OH. That's the important part. Bases have OH. And really, it's OH minus if it's not linked in with another thing in a compound. I do want you to be careful, though, very careful. If an OH is bonded to a C, it is special. It's an alcohol, not a base. It's an alcohol, not a base. For example, if I look at CH3OH, I'm going to notice that I see an OH. So I see this has a OH. Sorry, I put it back. I paused the video. I have an OH, and I have a C. So that alerts me that this is not a base. This is an alcohol. Because I see that this is an alcohol. Difference is if I see, for example, NaOH. Well, here I'm going to see an OH, but I don't see it with a C. So this is a base. This will be an important concept to know. Do not let them trick you by giving you an alcohol. Know if it's an alcohol or if it's a base. When we looked at table L, we also realized, I can go back, we also realized that if I look at this ammonia, this NH3, it doesn't look like the other bases look like. Because of that, I also have to have an alternative definition. Arrhenius says acids have H, bases have OH. That doesn't cover ammonia. So we have what's called the Bronsted-Lowry definition of acid-base. But very often, the Regents won't say Bronsted-Lowry, they'll say alternative, or they will say other. We'll just say it's the other one. Well, in the other definition, we say that an acid is an H plus donor. An acid is an H plus donor, where a base is an H plus acceptor. A base is an H plus acceptor. So that helps me define this NH3 as being a base. Because if we draw NH3, so we know it's a base. You draw NH3, you've got your N, you've got 3 H's, and there is 2 electrons on it. So these 2 electrons that you see right here would be looking good to someone like an H plus that doesn't have it. So it would accept the H to go on there. It has room for it. So I can tell that something will be a base if it has room for something else to go on. If you look at the example reaction that we have here, I want to look at how they were on one side versus how they were on the other. So I have HCl. On the other side, I have H2O plus and Cl minus. So these must go together. HCl and Cl minus. If I look there, I'm noticing that I lost an H. I lost an H, really an H plus. It's gone. I donated it. So I donated that H. If I look at the other one, then I'm noticing H2O became H3O plus. This has an extra H, so it accepted an H plus. I have one more. That would mean that this must be my base because it accepted, and this HCl must be my acid. It's important to note that I'm noting water is a base. Water is special. It can be both acidic or basic. So I have to figure out what it is by looking what happens on the other side. So whenever I go to figure out who's an acid or base based on the Bronsted-Lowry definition or the alternative, well, then I'm going to look at what happened to them on each side. If it lost an H or donated it, it's an acid. If it gained an H or accepted it, it will be a base. So we're flipping over to the next page, page 8. They're asking us questions that go with what we've just said. So they said, which is the proton or H plus donor? We saw that HCl donated it. And which was the proton acceptor? Well, the H2O accepted it because it turned into H3O plus. So that would make HCl, my acid, like I said, and H2O acting like my base. H2O is not a base all the time. That is very important to know. Not a base all the time. So I should define this for you. Substances that are amphoteric are things that act like an acid and sometimes like a base. They act like both an acid and a base. Water is our example. If I'm looking at this example, I'm just going to pick one of my waters. I'll pick here. So if I say this water turned into this, well then, if I look and I compare, this looks like it has an extra, so this would accept an H plus. And if I'm looking at this one, my H2O going to OH minus, I lost an H there, so I donated an H plus, which means that The first H2O would act like a base. The second one would act like an acid. So water can be both. That's very, very important. So we can kind of note on the side. Acids have H. Bases have OH. I can also put my alternative definitions. Acids have H, and they donate a proton, which is an H+. Bases have OH, and they accept your H+. Water is amphoteric. It acts like both acid and base. I also want to define what a salt is. A salt is always an acid plus a base that yields a salt and water. So we define what the heck is our salt. A salt is any substance that has a positive ion other than H, it can't have H, and a negative ion other than OH. So anything that has a positive and negative. So you really want to think that a salt is anything that is ionic. A salt is anything ionic, because ionics are metals and nonmetals. They form ions, positives and negatives. An example of this, if I look, I'm going to show you the acid plus base gives us salt and water. I have acid, let's take H2SO4, plus base, let's do CaOH2. Gives me a salt and water. So this is going to be a double replacement reaction. So in a double replacement reaction, remember the first thing wants to switch with the other first thing, so my H wants to switch with my Ca. That means that my H will go with my OH. I can do my little crisscrosses over here. My H plus wants to go with my OH minus, so I'm going to get H2O. I'm going to write it second. It really doesn't matter, but I'm going to write it second. And then my Ca wants to go with my SO4. Ca is plus 2. SO4 is minus 2. So when I crisscross, those twos cancel. I just get CaSO4. So if I'm looking here and I want to see, well, who's my acid, who's my base, who's my salt, who's my water, there's an H, so here's your acid. There's an OH, here's your base. So acid plus base, get my arrow. Here's my salt, because that would be ionic. And here's my water. These will be very, very important as we continue this. Very, very important. This back up here where it said acid plus base gives us salt and water. This is called a neutralization reaction. Neutralization. That is always the answer. Acid plus base gives you a salt and water. All right, so we're in there. We also have to do our characteristics of acids and bases. So we want to know a few things about them, starting with acids. So acids, just like we learned, acids react with bases to form salt and water, always. And I can write a few things about them. Acids taste sour. They have H plus or H3O plus. They donate H plus as that alternate definition. And they conduct electricity. That will be important to know. They will conduct electricity because acids and bases will break into their ions. That will be very important. So actually, I'm going to underline that. Acids and bases will conduct electricity. And then down here, number 2, they're talking about these two things, blue litmus and phenolphthalein. These are indicators. I actually don't want to fill this part out right now. I just want you to know that litmus and phenolphthalein are indicators. We'll do more with those soon. And now let's look at our bases. Our bases, we can do the same thing. A base reacts with an acid to form salt and water. I hope we're understanding that this will be an important equation. I've probably said it about 5 times already right now. Acid plus base will give you salt and water. That will be important. And our characteristics, bases taste bitter. Think like dark chocolate. They have OH minus ions, or I define them as being an H plus acceptor. Generally, if you get them on you, they're going to feel slippery. They will feel very slippery. Oops, I forgot. Well, you're used to me spelling things wrong. Slippery. They'll be slippery. And they conduct electricity. Sorry, I'm running out of room. They conduct electricity. I should probably also say right here, if I'm saying that these things conduct electricity, these are called electrolytes. You should have heard that word probably before, electrolytes. Most people think of Gatorade when they think of it. Gatorade or those power drinks, those have electrolytes in them. They are replenishing the ions that you actually lose when you sweat. That's why you drink them when you play sports. Or maybe you just drink them because they taste good. But either way, they conduct electricity in your body. And then bases also, we're talking about litmus and phenolphthalein. Again, we'll just say those are indicators. And we'll learn about them on another day. So I would say these characteristics of acids and bases kind of puts everything together. I might, in my notes, kind of try to draw my eye to this because it just sort of summarizes what we just said over the course of 2 pages. All right, we're almost done. Keep going. We are going to talk about our acid-base reactions. This won't take long, but we're going to your packet page 12, so make sure you move there. And on our page 12, the first thing we're going to write is our neutralization reaction. Neutralization. This is a double replacement. And it's what I said about 5 times. Acid plus base, arrow, salt, and water. That is always, always, always true. Always, always, always. Always the answer. Acid plus base gives me a salt and water. So let's try to figure out what's going on here. So I've got HCl and NaOH. Ooh, I see an H, I see an OH. This is my acid. This is my base. I don't even have to think about it. I'm going to make a salt, and I'm going to make water. So I don't got to think. Fill in H2O. You got it? I got to figure out who's the salt. Well, my H and my OH made my water, so my Na and my Cl must make my base. So NaCl. really, because Na is +1, Cl is -1, technically. And again, acid plus base give me salt and water. They tell me my acid or my base, I know what I'm going to form. I can do the same thing with the next example. I see H2SO4. H is in front. Here's my acid. I see CaOH2. Ooh, I see an OH. This is my base. And I know I'm going to make a salt and water. So I might as well just fill in H2O over here. I just got to figure out who's my salt. So it's between Ca and SO4. I better crisscross. Ca is +2. SO4 is -2. 2's cancel. CaSO4. And then you just want to make sure that you always are balancing these. So I need 2 H2Os. I might need more than that. No, 2. I need 2 of those to balance that equation. Acid plus base gives you a salt and water. And the last one I have to do, very last one, we're using table J. Table J. Look at table J. I'm using it there. When I use table J, these are always going to be my reactions of acids with metals. My reaction of acids with metals. Because acids have H, so metals will try and react with them. These will be my single replacement reactions. Which we have been doing. Remember, we always have to check table J if I'm doing a single replacement. So it said which 3 metals will not react with acid. Well, you want to remember on table J, higher replaces lower. And if higher replaces lower, well, which will not react? Anything lower. But it's got to be lower than your H, because your H denotes your acid. So which 3 metals will not react? Well, it'll be Cu, Ag, and Au. They say why? We'll say because they are below H on table J. So for your reactions of your acids with your metals, it says reactions producing hydrogen gas will denote, again, single replacement. So when I do these, I'm always going to have a metal plus an acid that will always give me, if it works, a salt and H2 gas. Metals and acids will react by producing hydrogen gas. So I've always got to check. I'm going to say, okay, can K react with HBr? Well, I'm going back up to my table J. Let's see if K is above H. Oops, this moved my little box. Here. Oh, it moved everything. That's okay. I want to see, where's K? Oh, K is way up here. K's up here. H is down here. So if I come back down and say, okay, K can replace H. So K goes where the H is, kicks H off. H is diatomic, so it must be H2. So now I got KBr. K is +1, Br is -1. You crisscross, you get KBr. You now just want to make sure that you are balanced. This is not balanced. There are 2 H's here, there's only 1, so put a 2 in front of that H. That means I now have 2 Brs, so I gotta go here, which means I gotta put a 2 here. The next one, Cu and HCl. Oh no, when I look, I'll see if I can get back up there. Cu is below H. So that doesn't happen. So no reaction. No reaction. Then I'm going to do Mg and HF. So Mg and HF. Just make sure, check table J. Is Mg higher? Yes, it is. So I say, okay, I know I'm making H2 gas because I always will. The Mg and the H are going to switch. Mg is plus 2. F minus 1. Crisscross. MgF2. That's my salt. And I gotta just put a 2 here. And I'm good. Last one. AU and H2SO4. AU's lower. No reaction. Woo! We made it. Thanks, guys. See you tomorrow. Get all your notes. Ask me questions. Have a good night.